Good evening, ladies and gentlemen. My name is Griffin Beasley, and I'm here to present my research project on combating delamination in additively manufactured parts. This research is conducted in the Department of Metallurgical and Materials Engineering under the supervision of Dr. Charles Monroe. Additive manufacturing is a very popular up-and-coming technology in the metallurgy industry. These processes use a three-dimensional digital model to fabricate a new piece through the deposition of a stock material onto a build platform. The parts made from this process can be made very accurately and very efficiently that almost exactly resemble the three-dimensional model supplied and have very tight tolerances, which are often not found in other manufacturing styles. There are many different kinds of additive manufacturing. They are typically differentiated by two main qualities: the state that their stock material is in and how that stock material is deposited onto the build platform. For this project, we will be using a powder-based stock material, and we will be melting said stock material onto the build platform. There are still many processes that fit under these two qualifications, but the one that best fits our intentions for this project is known as selective laser melting. Selective laser melting, or SLM, uses a high power density laser to melt the powder onto the build platform. After the current layer has been melted, the build platform is lowered and a new layer of powder is rolled out onto the build platform using a roller or rake. Like most additive manufacturing processes, selective laser melting is capable of making very complex parts very accurately. In addition, by finely tuning the laser's output, microstructures can be intentionally created during the process, which limits the need for post-process heat treatment. Also, chemical composition is almost perfectly maintained throughout the process. This means that the chemical composition of the powder that is put in at the beginning almost exactly matches the chemical composition of the finished part, which is another quality that is often not found in other manufacturing styles. However, there is one major drawback to selective laser melting and additive manufacturing as a whole, and that is something called delamination. Delamination is the separation of layers in an additively manufactured part. As pictured in the slide, the bonds between the layers break and the layers begin to pull apart from each other. Now, this is typically caused by two main things, and those are internal stresses during the creation process and incomplete bonds caused by porosity. As for what this does to the part, the most obvious thing is that as the layers pull apart from each other, the part itself begins to change shape and it no longer matches the provided three-dimensional model. This means that the previously expected accuracy and tight tolerances are no longer present in the finished product. But more importantly, after delamination occurs, a complete structural failure occurs inside the part, meaning that parts that experience delamination can no longer hold any kind of load without further delamination or complete breakage occurring. This means, with how common delamination is, that most additively manufactured parts cannot be reliably used in a high-stress environment. Our research seeks to prevent delamination and therefore open additively manufactured parts to more applications. We intend to do this by combining the selective laser melting process with a process known as forge welding. And our exact hypothesis is that if the methods of forge welding are applied to an additively part made from SLM specifically, then the part will have improved layer-to-layer adhesion and improved mechanical properties that will also change based on the ways that the layers are oriented. Now, this raises an important question. What is forge welding? Forge welding is the process of taking two or more pieces of metal, heating them, and striking them together with such a force that a bond is created between the two pieces, making them one solid piece. As pictured in the right side of this slide, these pieces have not undergone the forge welding treatment. And you can see that the layers are very clearly separated and differentiable, and the part is not homogeneous. Versus on the left side of the slide, this section has undergone the forge welding process, the layer lines are not very apparent, and the piece overall is much more homogeneous and solid. Now, how can forge welding apply to additive manufacturing? If you look in the bottom left of the slide, you will see one of the most common products of forge welding process, which is a type of steel called Damascus. Damascus is made by stacking multiple pieces of steel together, often which are different alloys, forge welding them, folding them over themselves, and drawing them out until a pattern similar to the one seen in the slide is created. In the slide, the dark gray and the light gray colors correspond to the two different alloys used to make this Damascus. Now, for additive manufacturing, we intend to view the layers in our part created from SLM very similarly to the layers used in a Damascus billet. And we believe that if we put this additively manufactured part through the same kind of forge welding process that Damascus is put through, we will see an improvement in the mechanical properties that the part possesses. Our procedure for these experiments is very efficient and simple, which will allow us to repeat it multiple times very quickly with multiple different alloys. Our first step is to select the alloy that we would like to use. We will then put this alloy through something called atomization. Atomization is the process of melting down a piece of metal and resolidifying it in a powder state. There is an atomizer facility here on campus that we will be able to use for this experiment. After we have obtained our metal powder and also a three-dimensional model, most likely of some stock piece such as the bar or a rod of preset dimensions, we will load them both into a selective laser melting machine and create our first test part. We will put this part through the forging process, and then we will extract test samples to be used in the testing for mechanical properties and some microscopy analysis. After we have obtained hard data values for our mechanical properties, we will compare these properties to properties of similar kinds of steel to try to determine exactly what effect the forge welding had on the additively manufactured part. For mechanical property testing, we intend to conduct two main tests, and those are the tensile test and the Sharpie impact test. The tensile test applies an opposing force to two different sides of the test piece over a prolonged period of time. During this period of time, it measures the stress and the strain that the part experiences, and from this data can calculate yield strength, ultimate strength, and percent elongation. These values together can tell us how the part will perform under a prolonged stress. The Sharpie impact test, on the other hand, uses a large pendulum to snap the piece in half. The potential energy of the pendulum at the height of its swing before it strikes the piece and after it strikes the piece are both measured, and the difference between these two values corresponds to the energy required to rupture the piece. From this energy, we can determine how well the part will perform under a sudden impact. For the future of this project, we intend to test with multiple different steel alloys and hopefully adventure into the realm of non-ferrous metals. And also, after we have obtained hard data values, we're going to try to determine where and how this process can best be applied. I will now take any questions that you may have.
So you talked about how additive manufacturing makes very intricate parts. I was wondering, so how do they not lose those intricate designs in the forging process and lose the tolerances associated with that?
So there's kind of a two-step process to that with our current layout of our experiment. For the first few experiments we're going to do, we're not going to be considering that very much, and the part we create is not going to be very complex, and we're not really going to be worried about how it changes shape. Because currently, we just want to see if our theory is really feasible and if we actually get a change in data from the forge welding process. If it is successful, what I think we could do is we could use a software that is capable of simulating the forging process and determining where the metal is going to move after it is being hammered. We can use this kind of software to sort of re-engineer the part and develop a 3D model that we can then hammer into the precise shape that we want.
I was curious, it sounds like you're creating a sample with SLM and then forge welding. What other steels might you compare that sample with, determine the mechanical properties?
So we have a couple idea of different things that we can compare our results to. The most obvious, of course, is a part made from selective laser melting of the same alloy that did not go through the forge welding process. And this will really be able to tell us how effective our prevention has been for delamination. But also, just for a little bit of extra information, we intend to conduct tests comparing it to just some standard cold-rolled steel of the same alloy, and also potentially some actually handmade Damascus of the same alloy as well.
Hi, so I have a two-part question. In your future plan slide, you mentioned non-ferrous metals. I was wondering what ferrous means and what non-ferrous metals you might plan to test with.
So ferrous is a term used to describe any metal that has a large iron content into it. So most steels, which are probably one of the most commonly used metals in the modern days, have a very large iron content and are therefore described as ferrous. For the non-ferrous metals that we intend to use, we're probably going to be looking at aluminum and titanium for the most part, because those probably have the most real-world applications that we would be interested in applying this process to.